Alright, hi everybody, welcome to Science 71 here on Wednesday, January 9th, day 81. I apologize that I'm not here today. This is a bit of a trial as we do have a couple of times in the year where this happens, but I want to let you know that I've left a lesson plan that I think is doable for you folks as well as successful heading towards the end of the week when you are going to have your vocabulary quiz. So, first things first, please respect the guest teacher, and please make sure that this video runs smoothly and full screen on YouTube. You should be able to go and load it, no problem. So, we go and head towards the next slide here, and I'm going to make sure that everyone's clear on what your homework is for tonight. This time, I'm not going to hand you a printout sheet that's already going to have your shapes on and so forth. You're going to need to produce your own top-down web on Chapter 2, Section 1. Now this is the start of forces. Okay, start of forces. You will note there are some pages that needs to be read as well as some questions on page 49 that I'd like you to answer on the back of your top-down web. These are all just standard steps that we're going to become more familiar and routine in our class as we move through the remaining units of the year. So, here we go. You also have your quiz on Friday. Please do not forget your vocabulary quiz on Friday. It's very important that you become familiar with these terms, practicing vocabulary puzzles. There's puzzles in the middle of the table that you can use. There's also computer paper and white line paper that you can use to go and make flashcards if that works for you. Alright, so our objective is to begin really focusing on how motion and forces are connected, how a force can create a motion, and how motion can create a reciprocal force. We're going to be talking about Newton's laws as well. In student terms, very simple, how is motion related to forces acting upon an object? And what happens when there is more than one push or pull acting upon an object? Our agenda, we're going to cover Chapter 1-1 and 1-3 in the form of notes. You will have a quick handout that's going to be passed out with you when you walk into class today. You are free to write on. Use this paper to go and finish your notes and keep this with your C layer as you can refer back to it. We're going to discuss some layers as well as go over the lesson of the day, which is C1 and C3, and we will be collecting and checking the homework from last night. First things first, conversions. So you already saw in Chapter 1-1 we talked a little bit about the SI unit, the system of international units. The main ones we talk about, meter, liter, and gram. Today, for purposes of motion, we're going to focus on the meter or length. And so the main one we're going to focus on is the meter stick. Alright, so the meter stick has 100 centimeters in it. As you can see on the screen, 100 centimeters. So the meter stick is broken into 100, and within each centimeter there is 10 millimeters. So, quick bit of math, 100 centimeters times 10 millimeters is 1,000 millimeters per meter stick. You'll also note at the very bottom here we have 1 kilometer is equal to 1,000 meters. Kilo, 1,000. Keep that in mind when we head into the next screen. Would you please pause the video, take a few moments here to see if you can figure out what are the conversions in each one of these blanks that is listed on the screen. Pause the video. Alright, so we're back. Let's check our answers. We've got a couple of things here going on. Most and foremost, we have this issue of converting from meters to centimeters. So you'll remember that's a notion of 100 cm per 1 meter. Well, if I've got 3.5 meters, what do I have? You got it. 350 centimeters. Conversely, if I only have 50 centimeters, that's roughly half a meter stick, so our answer here would be 0.5. Nice. 25 centimeters. Now this one's a little bit of a trick. We have to go from centimeters to an even smaller unit, millimeters. So you say to yourself, 1 centimeter has 10 millimeters. So 25 times 10, 250 millimeters. Nice. Go a little further down the line here. 4 kilometers. Well, got to remember, 1 kilometer has 1,000 meters. And so, how many meters will we have here? You got it. 4,000 meters. 3,300 meters is equal to how many kilometers? Same equation as before, we're just going to reverse it. In this case, we know there's 1,000 meters per kilometer, so we move the decimal 3 places. Bam! 3.3 kilometers. And there's your answers. Wonderful. Hopefully you've gotten that. Moving on. So, motion and reference points. This idea that things are in motion is strictly based upon the idea that we have to have a reference point that we're using to determine whether or not there is motion. A distance between two objects is changing. The example I may have mentioned before is the elderly woman sitting on a bus rolling down the street, passing a man standing still at a bus stop. In one instance, she is moving, and in another instance, she's not. It all depends upon what your reference point is. So, here we are. We're now up to speed. We've got to start memorizing these formulas. This speed is distance per unit of time. S equals d divided by t. Given that the school bus with a flat tire traveled 10 miles in half an hour. Now, I know the bus should have stopped and changed the tires, but go along with this here. What was the bus's speed? Was it 10.5 miles per hour? Was it 0.5 miles per hour? Or 20 miles per hour? Pause the video. Do the math. Thanks for pausing. All right, so the question now still stands. What is the speed of this bus? Well, you know that the bus is going a grand total here of 10 miles in a half hour. And so our rate is 10 divided by 0.5, which does equal 20 miles per hour. Awesome. Correct answer was C. Well done. Next up, average speed. Please make sure that this is somewhere on your paper there. But at the same time, could you also try and figure out the question below here? We have a rabbit that's traveling 40 meters in 5 minutes, resting for 5 minutes, and then sprinting 10 meters in 1 minute. And then we also have a turtle starting at the same time, traveled 50 meters in 10 minutes. What was the average speed of each, and who won? See if you can figure it out. Pause video, I suppose. Now, as we're heading through this idea of fast as a rabbit here, I believe the rabbit was 40 meters, and what was his remaining distance there he had to travel? 10 meters. Thank you. Now, what was his total time? Well, his total time, I think, was 10 minutes. Oh, no, sorry. Gosh, I need to go back on my screen here and figure that out. We'll pause for a moment. Alright, figured it out. It was 40 minutes and 5 minutes. So, sorry, 40 meters. And he did that in 5 minutes. But then he rested for 5 minutes. And then he sprinted for 1 minute. And I believe that last 10 meters is when he did that 1 minute. So that's the rabbit. So you have a total here of 50 meters divided by a total time of 11 minutes. Now the turtle, if I'm not mistaken, was 50 meters and he did it in exactly 10 minutes. So between the two of them, we now have our average speeds as well as we know who won. In this case here, the turtle did win. The turtle was able to go and cover the distance, the average speed-wise, faster. Cool. Alrighty, velocity of a fish. Velocity. We've talked about speed already. Speed we now know is pretty much distance divided by unit of time, but we need to talk about velocity. And velocity is a speed in a given direction. And so we got in a couple examples right here. The car moved at 50 miles per hour east. And the big thing here is that we've included a direction. And so please make sure you can distinguish between the two. If we go to the next slide, we have a scuba diver here relaxing near a coral reef. You notice the tidal current moving to the right, and you see a school of fish swim to the left. From your perspective, the perspective of you not moving, what is the velocity of the school? And I think it should be noted that the two items here are moving in opposite directions. Tide is moving to the right, school is moving to the left. I'll give you a couple seconds here to see if you can figure out what is the speed and the velocity of the school. You can pause the video if you'd like. Chat amongst yourselves, partners. Alright, so we're back. So we have to figure out here, what is the speed, better yet, the velocity of the school? Well, if we have a velocity of 1.4 to the right and a velocity of 2.7 to the left, well, we're going to need to basically subtract these two numbers. So 2.7 minus 1.4 is 1.3. And what's the direction? 1.3 meters per second, and this here is to the left, or in this case here, west. So that is our velocity. Hopefully you guys got something very similar. The big thing here is we need to count for both the tide flow as well as the speed of the school. Cool. Let's press on. Common formulas I'd like you to start memorizing. You'll notice here, ladies and gentlemen, that I've listed average speed, average velocity, and now I'm going to start heading into acceleration. So acceleration is a little bit different. This kind of relates back to what you did for homework last night in chapter 1-3. But acceleration is a velocity final minus a velocity initial divided by time. And I'd like to kind of help people understand that the term initial means beginning and final means end. Keep that in mind when you're working on the next problem. So, in your notes, we have this idea of putting in some more information. It's already on your paper there. But please star it, highlight it, whatever you need to do, and kind of remind yourself that in science, acceleration is one of three things. It's speeding up, it's slowing down, or it's changing direction. And therein lies this idea that you've probably experienced acceleration numerous times and never really known that you were actually accelerating. Let's take the example at the very bottom there. Is the moon accelerating? Take a moment to think about it. Is it accelerating? Ask yourself the questions. Does the moon speed up? Does the moon slow down? Does the moon change directions? Looking at this very briefly, really quickly you can kind of see, does the moon speed up or slow down? In a nutshell, I'm going to leave them as no. There is a little bit of acceleration that occurs when the moon is either closer to the Earth or farther away, but the orbit is not elliptical enough for us to really notice this difference in speed. However, when it comes to changing direction, at any point in time, the moon is changing direction as it moves around the Earth in its orbit. And so, even though speed is not really a factor, we can say that the moon is accelerating due to change in direction. So keep that in mind when you're thinking about acceleration. It's not always about speeding up or slowing down. So, let's see if you can try this equation. We have a plane that is headed to Hawaii and it starts at rest on the airfield, this airport. 2 hours later, at the end of the runway, it's traveling 300 miles an hour south. So what is the acceleration that this airplane... this is actually really a bad question. Hold on. So we fixed this question. I apologize. If it's sitting on the airfield for 2 hours later and it's only doing that, I'd be a little upset about the flight taking that long. So let's try it again. A plane headed to Hawaii starts at rest. 2 hours later, it's traveling 300 miles an hour south. What is the acceleration? Well, we should remind ourselves to keep in our mind that we have to find the final velocity, the initial velocity, and the time. And so we'll start off with a notion here of getting 300 miles per hour. That's our final velocity. And our initial velocity is 0 because it was at rest. That's how it started. How long did that take? It took 2 hours. So, what's going to be our acceleration? Our acceleration is going to be 150 miles per hour. It's important to remember this hour per hour deal. As you can see on the screen here, we have two areas where we've got time. We've got time above and we have time below the division symbol. And this is above, this is below. So we want to make sure that we keep that going. So this is the difference between an acceleration and a speed. An acceleration has 2 units of time, and a speed would only have 1 unit of time. Alright, keep that in mind. Awesome. So, I'd like to take a couple moments now and correct last night's homework. If you could please take out the homework. We'll go over the 4 questions quickly, and you will go and turn this in. Alright? Please go and get your homework out. So it was just brought to my attention there's only a couple moments left before this video runs out. And so the answers I'll leave up here on the end here. But please note, between speeding up and slowing down and changing direction for 1, you can find the equation back on page 36. The horse trotting around a track, it's going around and changing direction. And number 4, working on the same idea of getting to the number 24, 12 to 2, 4 to 6, anything that gets you 24 will work fine. So folks, the remainder of class is for you to work on your C layer and for your homework. Please respect the teacher. I will see you as soon as I can. Take care.